G'day. In the previous video, we started to look at our 5 kinematic equations. In this one, we're going to look at some methods that we can use to derive those kinematic equations. So we're still looking at dot point 1.1.5. This is our last part of inquiry question 1, looking at being able to predict and describe the motion of objects going in a straight line. Our kinematic equations here are really good at being able to predict certain elements of motion if they have not been measured. We've already begun to start to look at how we can use those kinematic equations and apply that element of prediction. But today our focus is going to be looking at this section of our content statement, which is deriving those relationships and actually looking at where these kinematic equations come from. So our learning intentions for today, we're going to derive our kinematic equations, and I'm mostly going to be using some graphical methods. So there will be a velocity time graph, there'll be some analysis that we can undertake based on different kinds of variables, and from that information be able to come up with our kinematic equations. Some steps will also require some algebraic methods to be able to find or derive these kinematic equations. What I'll also be showing you today is some methods that we can use to be able to determine the 2 kinematic equations that aren't in your data sheet by using the 3 that are given in the data sheet as well. So that way, if you are under exam conditions and you only have the data sheet in front of you, you do have a way to be able to find and determine those other equations so that you're able to use them. So what we're going to do first is derive our first kinematic equation, the more simple one. V is equal to u plus at. And to do that, I'm going to be using this velocity time graph so that we can do some geometric analysis. So what I'm going to put in first is u and v here. So we can see that u is a non-zero value on this graph. I have selected a velocity time graph like this for a reason, and that mainly is so that u is a non-zero value. V, our final velocity, is a little bit higher. So we see that there is an increase of velocity over time. Now, to determine our v equals u plus at equation, the mathematical information that we need to remember and use here is that acceleration on a velocity time graph is essentially the gradient. In other words, it's going to be equal to the rise over run. So I'm going to do some annotations on our graph to sort of show that idea. So here our rise is going to be v minus u. So the final velocity take away the initial velocity is going to be our rise, and the time or the duration of time to get from u to v is going to be our run. So if a is equal to v minus u, our rise, divided by our run, which is t, this is already an equation that we have begun to use to calculate for acceleration. What we haven't done is rearrange that equation. So what I can do is take t and move it onto the same side as a, so get at is equal to v minus u, and then move u over to the other side as well to make v the subject. So that gives us u plus at. Now you'll notice that v equals u plus at essentially is just a rearrangement of a equals v minus u over t, where v is now the subject. So that's our first equation, quite simple to be able to determine that one. Our second kinematic equation is S is equal to ut plus half at squared. When we started doing some problems in class, I did introduce the concept that displacement is equal to the area under the curve of a velocity time graph. Effectively meaning that if we are able to find the area of all of this under the curve, we are able to determine the displacement of the object in motion. Now, there are a couple of ways that we can calculate and determine the area underneath that curve. The first way, and the way that we're going to do it for this kinematic equation, is by splitting our curve into 2 familiar sections. We now have a rectangle and a triangle. And so what we can say is that the displacement is going to be equal to the area of the rectangle or the quadrilateral plus the area of the triangle. To be able to calculate those areas, we need to know the values of the dimensions, even from just an algebraic perspective. So some things that we already know about this graph is that our top point here is v, the final velocity. Our bottom point here is u, the initial velocity. And our distance from u to v along the x-axis is our time. Keeping this in mind, we can now begin to figure out the dimensions of each of our two-dimensional shapes. So our height here of our triangle is going to be v minus u. Height of the rectangle is just going to be u. And we've already actually written down the length of the base of the triangle as well as the length of the rectangle. Both are t. So what that means is for the triangle, the area of the triangle can be calculated as half base times height. So half times v minus u times t. And the area of the quadrilateral, the rectangle there, can be calculated as simply u times t. I can put those areas into our displacement formula. So that's going to be ut plus half v minus u times t. Already we should start to see that the formula is taking a very similar shape to our second kinematic equation, but we're not all the way there yet. The way that we can get acceleration into this equation is using our first kinematic equation. So if I were to solve and get v minus u on one side, in other words, I can write here v minus u is equal to at by simply moving u to the left-hand side. I can substitute at here into my equation, into the part of the equation which has v minus u. When we do that, we get ut plus a half at times t. In other words, s is equal to ut plus half times a, and because t times t is t squared, we can simplify that part of the equation there. And there you go, we have our second kinematic equation using some graphical methods, adding up to areas in our velocity time graph. Now for our third kinematic equation, this is one of the ones that does not appear in our data sheet, but we can use graphical methods to figure it out. And again, I'm going to use this idea that s, our displacement, is equal to the area underneath the curve of a velocity time graph. However, I'm going to calculate area a little bit differently this time. Instead of breaking up the area into two parts, I'm just going to use the entire area that's given and calculate it all at once. Reason being that the shape that I've just drawn out is actually a trapezium, not one that you usually see, but it is a trapezium nonetheless, and I guess you could imagine it to be sideways. So when trying to calculate the area of a trapezium, it's really important to keep in mind all the different parts before looking at the formula. So when we're doing area of a trapezium, our short side of the trapezium is A, the long side is B. We also need to know the height of the trapezium as well. Now the formula for that is A plus B over 2 times height. When we're looking at the trapezium that we have, A here is the short side, B here is the long side, and time is representative of the height. Again, our trapezium is just sitting sideways. You may or may not have seen before a trapezium with a right angle for one of those sides. We still use the same formula even if it is a right angled one. Before we start calculating, I'm going to insert some of our data. So we know that our bottom point is u and our end point here right at the top is v. What that means is that a in the trapezium is equal to u, b in our trapezium is equal to v, and h in our trapezium is equal to t. Hopefully we can see that that makes our proof quite straightforward, and that is that s is equal to u plus v over 2, just like the a plus b over 2 part of our area formula, times t, which is there in place of our height. Something to note as well, the form of this equation here is quite similar to our velocity average calculation that we can do. So when we have a constant acceleration, we can just take the initial and final velocity, divide by 2, and that will give us an average velocity of an object in motion, again, when we have a constant acceleration. This is a topic that we've covered a little bit in class by this stage, but it may be something that you recognize in this equation. Note as well that if we do have a velocity and we multiply that velocity by time, we will end up getting the displacement, and that effectively is just a rearrangement of our velocity equals displacement over time equation. But just some little tidbits that can also begin to show where this equation has actually come from and why it actually works. This next equation is a little bit more tricky to derive. There isn't a great way to show a geometric representation of where this equation comes from, but we can use a little bit of algebra, combining equation 1 and equation 3 together to make our formula here, v squared is equal to u squared plus 2as. Now, in this case, what we should be able to see for this equation is that there is no t value. What that means is we want to take equation 1 and 3, solve for t for one of those equations, and put all of the other values into the other. So a little bit hard to explain, especially if you've never seen it before. So I'm going to run through the process. I'm going to start with v is equal to u plus at. And what I'm going to do is rearrange for t. So to do that, I'm going to first move u over. So v minus u is equal to at. I'm then going to get t as the subject. So t is equal to v minus u on a. And this equation is quite powerful because I can take this value and put it into our third equation here. And so when we sub v minus u on a into the spot where t is, it's going to remove t completely from that equation and just leave us with v, u, a, and s, which means that I can rearrange the equation so it looks like our fourth kinematic equation there. So I'll show that working here. So s is equal to u plus v over 2 times t. And when I substitute in t, that's going to be u plus v over 2 times v minus u over a. Now, combining those two fractions together, that gives us s is equal to u plus v, all multiplied by v minus u over 2a. You may recognize this from previous work in maths as difference of two squares. Now, because this is difference of two squares, it's really easy to expand those values. The numerator is going to effectively turn into v squared minus u squared, and that's going to be over 2a. From here, we can move 2a up, so 2as is equal to v squared minus u squared, and then we can make v squared our subject, so v squared is equal to u squared plus 2as. And there we go, we have now our fourth kinematic equation. Last kinematic equation here is s is equal to vt minus a half at squared. You should notice that it is extremely similar to our second kinematic equation. And that is because we can find it geometrically in a very similar way. So we're still going to have an area of a rectangle and area of a triangle to work with, but the rectangle in particular is going to be different. The rectangle is going to cover all of the space from time 0 to our end time here where v is, and from 0 velocity to our velocity v. And instead of adding two different geometries together, we're actually going to subtract them. So we've got our big rectangle there, and then we're going to subtract our area above the curve instead. So when we take the area of our big rectangle that we've drawn out and take away the triangle that is now above the curve, that's going to give us all the area under the curve. So in this case, we still run with that s is equal to the area underneath the curve of our velocity time graph. But this time we're going to say that s is equal to the area of the rectangle, take away the area of the triangle. We still have our u, our v, and our t. We can say that the area of the rectangle is equal to, this time, v times t. So that's our height here, v, and t along our x-axis. And that the area of the triangle, while technically it's not in the same position as our triangle from before, the way that we calculate it is exactly the same. This height here is still v minus u, and our length across is still t. So the area is going to be half v minus u times t, or half base times height. We can then substitute all of that information into our equation. So that's going to be vt minus half v minus u times t. So looking really similar again to the first one, some subtle differences. Again, we're going to write an expression for v minus u, again using our first equation and having that as at when we arrange our first kinematic equation. We can then take at and substitute it into v minus u. So we can write that as vt minus a half at times t. And again, to simplify the expression, we can have s is vt minus a half at squared. And there we go, our fifth kinematic equation done. Now, I also want to be able to show you how to find the third and fifth kinematic equations, which are not in your data sheet, but not using a graphical method, but instead using the equations that are available to you in your data sheet. The first one that we're going to do is S is equal to U plus V over 2 all times T. Now, to be able to calculate this, what we want to do is have an equation where there is no A, no acceleration. So that means that we want to be able to remove A. The way that we can do that is solve for A in one equation and substitute that solution, that expression, into another. Now, the way that I found it the most simple and straightforward was to use these two equations, so our first and second. This time I'm going to solve for A using S is equal to ut plus half at squared. I'm going to substitute into V is equal to U plus at. So starting with S is equal to ut plus half at squared. I'm going to solve for A first by moving ut to begin with, and then moving the half and the t squared over as well. What I can do is then take all of this, our expression for acceleration, and substitute it in for the acceleration in our first kinematic equation, v equals u plus at. The first thing that I'm going to do is to cancel out the t here. That leaves us with 2 times s minus ut on our fraction. I can then expand the brackets on the numerator. So that's going to be 2s minus 2ut all over t. And then what I'm going to do is separate the two terms on the numerator of the fraction. So that's going to be u plus 2s over t minus 2ut over t. That leads to a little bit more cancellation on t. And we're left with u plus 2s over t minus 2u. We then have two like terms. We have u and negative 2u or minus 2u. We can actually put those together, and what that will give us is that v is equal to negative u plus 2s on t. Now, the only thing that we need to do from there is to solve for s. So v plus u is equal to 2s on t. And then we can divide by 2 and multiply by t. So v plus u on 2 times t is equal to s. And then we're able to get our third kinematic equation by combining two of the formula that are in your data sheet. Final one that we're going to look at today is being able to find our fifth kinematic equation, again, using what's available to us, our 3 equations in the data sheet. In this case, what we have is no u, so no initial velocity in the formula. What that means is we need to use the formula that we have to remove u. To remove u, what that's going to require from us is to solve for u in one equation and substitute that expression into the other. In this case, I found it easiest to solve for v is equal to u plus at and sub into s is equal to ut plus a half at squared. So I'll solve first. That one's pretty straightforward. It is u is equal to v minus at. So then I can sub u, in other words, v minus at, into the u part of our second kinematic equation. So that's going to be s is equal to t times v minus at. That's in place of our ut term. And we're going to add on, as always, our half at squared. Now, expanding our brackets, that gives us vt and minus at squared. We can then add on again our half at squared. Now, something that's really interesting but could be a little bit difficult to recognize is that negative at squared and half at squared are actually like terms. So all we need to do is combine those two. So we have effectively negative 1 AT squared, and we're adding on half an AT squared. Now what that's going to give us is negative half AT squared, and that's essentially the resolution of adding those two terms together. We still have our VT there at the front, and there you go. We have S is equal to VT minus a half AT squared. Again, a way of deriving this equation using the three equations that you have available to you. Thank you very much. The next time we look at a content video, we're going to be moving on to inquiry question 2, where we start to begin to analyze and predict the motion of objects in a plane. In other words, objects that are moving in 2 dimensions. To do that, we're going to have to begin to look at analyzing vectors that are in 2 dimensions. That's going to take a little bit more concept, a little bit more mathematical work, but something that we can work towards starting in our next video. I'll see you then.